we can try. We can try a case. Let's take a very simple case, P1, P2, P3, and let's say here it's going to be 1, here it's going to be 2, and here it's going to be 4. Okay. Now, if x takes 1, yeah, we are left with 2 piles with different coins. So if x voids 1 pile, then y will just equalize the other 2 remaining, and we are in the previous situation, and y wins. So x has absolutely no interest in taking all the coins from 1 pile. So then again, if he cannot take anything from P1, if he takes something from P2, let's say he will take 1, let's say this will go to 114, then y can just take all 4, and x is left with 1, 1, and you remember this is a losing situation. Good, so x cannot take anything from P2. Now x can take from P3. How much or how many coins can he take from P3? If he takes 2, we get 2, 2, the same situation. If he takes 3, we get 1, 1, the same situation. So he only has one choice, choosing 1. 1, 2, 3. And now y, whatever he takes, from wherever he takes, he will either void 1 pile, or he will either equalize 2 piles. So he loses. Now imagine that the initial condition would have been, let's say, I would write here, would have been 1 to 100. It's the same situation. X can just take the system into 1, 2, 3, and y loses again. Okay, this was easy, but how about if I make 4, 19, 100? So you can see it's much harder now to see what you should take and what you shouldn't take. You can define this intermediate state. You can say, okay, 1, 2, 3, it's a losing state. I need to get him into 1, 2, 3. So if 1, 2, 3 is a losing state, and 0, 0, 0 is a losing state, what do they have in common, these losing states? Well, we saw also that, so let's see here losing states. So obviously 0, 0, 0 is a losing state, because if you are the last player and you don't have anything to take, you lost the game. Another losing game that we saw is 0, 10, 10. Because if you are forced to take from 0, 10, 10, of course, here it can be an indefinite amount of zeros. Your opponent can just keep the number of coins in one pile equal to the number of coins in the other pile, and you slowly but surely lose. Another state, losing state, is 1, 2, 3. Because whatever you take, you get into this similar state. Now, what do these have in common? We can see here we have equality. Here, we don't have equality. Let's make some additions. You know, try like in the last problem. Let's say 10 plus 10 is even. 1 plus 2 plus 3 is even. So you might think that, okay, if I am in 1, 2, 3, so if I have the total number of coins in all the piles, if the total number is even, this is a losing state. No, it's not, because remember what we talked about it. Remember that 1, 2, 4, and you have 1 plus 2 plus 4 equals 7. It's odd, and this is a winning state. Yeah, we have this winning state here. So it's much more complicated. I'm sure, oh, I mean, we kind of have an intuition that it reduces to odd, even, it reduces to equality. But however, being able to take all the possible, you can take either an even, either an odd number from a pile. It matters from which pile, so it's more complex than we actually thought. Now, one way to go around this, and I obviously didn't think about it and I failed to solve the problem before I saw the solution, is that, okay, I cannot tell anything about these numbers. How about I decompose them into something um, and look at those parts? So let's say, what is the, so I'm looking, for example, at chunks, and I'm saying it only makes sense to take those chunks. I mean, if you take um, something in between those chunks, is just, it's not. So for example, let's say um, the chunks are 1, 2, 4, 8, 16, 32. So this is a way to decompose a number. So whatever number you have, you can write it. For example, let's get a number quickly, 47. 47 equals to 32 plus, which is to the power of 5, plus we are left with 15, so we get plus 8 to the power of 3, plus 7, which is 4 to the power of 2, plus 2, plus 1. So we can decompose a number in sums of powers of 2. So let's write these numbers here. Let's say 10, 10. So 10, 10, I'm just going to write it horizontally. So when I see 10, I'm going to write it's to the power of 3 plus 2 to the power of 1. So it's 1, 0, 1, 0. This is the binary representation of 10. For the other 10, you get also 1, 0, 1, 0. And whenever you take something from a pile, you just modify these bits. So you choose a line and you modify it to your I don't know what in whichever way you please. Now if we add this bit by bit, we get here 0, 0, 0, 0. The sum is odd. Now if we look at let's say 0, 0, obviously we get 0, 0, 0, 0. If we look at 1, 2, 3, we have 1, 0, 1, 2, which is 1, 0, and 1, 1. So if we add them together, we see that you get 0, 0. So I don't know how the idea should have popped to you to write the binary representation of the numbers. But whenever you don't feel the numbers, you just might have to write them in a binary representation or in another decomposition. So this problem is solved by writing the numbers, the number of coins in each pile as binary numbers. And this is the way to get the transformation invariant. So once you know that you are looking for a transformation invariant, you might try crazy stuff. Look at the binary representation, look at the but since there are 7 players, 2 players playing the game, and from this from these special cases here of losing states or winning states, you might have this crazy idea of looking at the binary numbers. So now let's play an in game. Let's say I have, what was the state? 4, 19, 100. Okay, let's make it a bit smaller. 4, 15, 12. It's equally complex. So if we write 4 as being 0, 0, 0, 1, 0, 0, 15 as being 1, 1, 1, 1, and 12 as being 1, 0, no, 1, 1, 0, 0, we can look here and see that this is 0, this is 1, this is 1, and this is 1. This is the sum. I'm just going to, okay. So 4, 5, 4, 5, 12, I can even write it like this, 4, 15, 12. And I can put it over here. Okay, it's not perfect, but get the idea. Good. So 4, 15, 12. Now the thing is, I have the power as player 1 to modify one pile from here, whichever pile I want, in order to set this this number to 0, 0, 0, 0. The XOR sum. This is how it is called. Well, I can modify 12, I can modify 15, I can modify 4. Usually you have the most freedom in modifying the biggest number. I mean, you can modify absolutely every single bit of the biggest number. For example, if you wanted to modify the first bit of the sum by modifying 4, you had absolutely no control. By all means, you can modify 4. But let's say, in this case, but let's say we want to modify 15, which is the biggest number. So I will put here 0, I will put here 0, and I will put here 0. And you will get 0, 0, 0, 0. And already P2 is in a losing situation. Whatever he does, whichever number he modifies, let's say he modifies, so now this will be 8. Let's say he modifies 12. He just makes here, I don't know, he puts here 0, and he puts here 1. So he makes 12 to be 5. Now, if he makes 12 to be 5, the new sum, XOR sum, is 1001. So you have control over 8, and you can make this 0, and you can make, oh my god, you can make this 1. And again, the XOR sum is 0, 0, 0. And slowly, so you can make this 1, by the way. Slowly and surely, your opponent is forced to deal with a 0, 0, 0 situation, and in the end, he will be left with no coins to take, and he will lose the game. So the invariant of the transformation in this case was not so obvious to see. You had to look at the binary representation. Okay, so that's all I wanted to talk to you about today. So have fun and stay geeky.